with each small unit or episode, we're getting closer and closer to the model of learning. In this module, we'll try to define it. What is learning? Yeah. Okay, I will give you my digested definition or digested way. PAC learning, probably approximately correct learning. So, unbounded delta. In the last lecture and in the recap, we defined probability of getting a training set on which optimal hypothesis will lead to failure in the true loss, right? And that's the bound on the right. Our delta is the probability in question, because delta is exactly the probability of getting a bad training sample, which is just that. So we have upper bounded delta in our previous lecture. Yes, that's it. Probability of getting a bad sample is less than or equal to the size of the hypothesis set times e to the power of our accuracy parameter times number of samples. So let's divide left and right sides by delta, and we'll get this. That's clear, the sign doesn't change. Then let's apply log to both sides of the inequality, and since log is monotonically increasing function, the inequality sign doesn't change. So we end up with the right hand side, which is non-negative. It's greater than or equal to 0. Log of the ratio of our size of hypothesis set over delta minus epsilon m. Epsilon is our accuracy parameter and m is the sample size, number of samples in the training set. So from that we can rearrange and obtain this inequality, which just says that accuracy parameter epsilon is inversely proportional to the number of samples m. What we mean here is if you fix epsilon, then given the rest, you need more samples in order to get that epsilon. You need to increase the number of samples. Another question is, for a fixed delta and epsilon, which m should we take? How many samples should we take in order to achieve a given probability of getting a bad training sample and a given accuracy parameter, a given accuracy? That's this. We should take at least log of the size of our hypothesis set over delta over epsilon samples. At least that's what this inequality says. Take at least this many samples, and you will guarantee delta and epsilon. And okay, higher number of samples will lead to better chances of increasing 1 minus delta. Okay. So from that, what follows is, given a finite hypothesis class, a fixed delta in the open interval 0 to 1, so it's between 0 and 1 but cannot take either of the values, and a non-negative, or sorry, positive epsilon greater than 0, and number of samples more than or equal to the bound that we just established for any labeling function and data generating distribution, but for that realizability assumption must hold, with probability at least 1 minus delta over IID samples in our training set of size M for every empirical risk minimizing hypothesis HS. Our true loss will be less than or equal to epsilon, or success. We will be successful. From that, we can define PAC learnability. A class of hypotheses is PAC learnable if there exists such an M for this class that belongs to such an M for this class, which M sub H is a function. It's a mapping. Basically, look here, you will understand this notation better. It's a function that takes values on an open unit square. Let's say this is epsilon, this is delta. So M takes epsilon and delta, look here, and returns a natural number. Okay, so H is PAC learnable if there exists such a function M sub H and a learning algorithm with the following properties. For all epsilon and delta in this unit interval, for all data generating distribution and true labeling function, and for all data generating distribution over the domain chi, and for all labeling function f that map a sample in the domain chi into either 0 or 1, when realizability assumption holds, when running on M greater than M sub H function's value, IID samples, the learning algorithm returns a hypothesis S such that probability of success. Remember, this is probability of success because our loss is less than epsilon, is greater than 1 minus delta. So this definition was given by Leslie Valiant in 1984, and what it defines learnability of a class of hypotheses. And in our previous lecture, lecture 2, we established that it should be a finite class. So to make it a finite class, we have to somehow structure it. And hypothesis class could be the class of models, for example, linear hyperplanes, polynomial curves, etc. In our two-dimensional example, our hypothesis class could be class of rectangles on a grid to make it finite. Okay, PAC learnability. Another interesting, so that's how we define a PAC learnability. But another interesting notion is sample complexity. So computer science is all about complexity of algorithms, right? We have running time complexity, we have space complexity, and we organize algorithms in different classes of complexity, such as polynomial, non-deterministic polynomial, p-space, and many others, the whole hierarchy of computational complexity classes. But when we start talking about machine learning, there is another notion of complexity, and when we want to talk about learning from examples, from data, we need to define the notion of sample complexity. That means how many samples does one need in order to generate a classifier that would perform well on a particular problem. A classifier from a particular class. So sample complexity is a function of epsilon and delta. This is m sub h. And it tells us how many samples are required to guarantee a probably approximately correct solution. So in fluffy words, what I just said before this phrase, it was about how many samples we need to learn correctly, but what does it mean to learn correctly? It's undefined. So to define everything, we can just use PAC learning. How many samples do we need to get a probably approximately correct solution defined through PAC learnability? So many of those functions satisfy the definition. So to specify just one function, we add a modifier. So sample complexity is the minimal integer. Sample complexity is the minimal integer that satisfies the requirement of PAC learning with accuracy epsilon and confidence delta. How's that for definition? What would sample complexity be for finite hypothesis classes? Think about it. Let's well, think about it before we go to the next slide. So sample complexity for finite hypothesis classes will, as you recall from one of the previous slides, we already established. So once we have this inequality, and we can establish the following inequality. So we bounded the delta and we were able to derive for m. For infinite classes, it's not finiteness, obviously, but another measure determines the learnability. But for finite classes, we can compute h, and our sample complexity, I said it wrong. It's not that we can compute h, but we can compute cardinality of h, number of possible hypotheses in the class. So we need a finite class. And basically, by taking the ceiling of this ratio, we can determine the minimal number of samples that we need to take in order that satisfy that our chances of getting a good sample are 1 minus delta. So the more samples, the better this quantity, 1 minus delta. Well, now let's recall your previous binary quiz from lecture 2 and go through the answers, because that's useful. So what do we mean by a learner? What is a learner? A learner is a process of turning training data as, set as, into functions or classifiers. Simple. What is generalization error? Our generalization error is probability of randomly, or according to the data distribution, of course, choosing an example X for which our hypothesis is not equal to the true labeling. The value that our hypothesis or classifier returns is not equals to the value that true labeling function would return. What is overfitting? Overfitting is when we have excellent performance on the training set and poor performance on the real world, or when we perfectly minimize the sample risk or empirical risk, and we don't perform well on the true loss or true risk. What is a fundamental question in learning theory? Which hypothesis classes are empirically which hypothesis classes empirical risk minimizing learning will not overfit? Okay, good. Now we know how to work with finite classes, and we know how to use inductive bias by limiting the number of hypotheses in a class, for example. But binary classification is not the only learning problem that we're interested in. We need to do something else, or go somehow beyond the binary classification into other problems, and still have a good sense of sample complexity that we need to achieve in order to achieve given accuracy, or given probability of not getting failure, or of probability of not getting a bad sample. So, for example, regression is one of the problems, right? That we are interested in machine learning and in natural sciences, and we'll talk about it in a little more detail later. So, to go more general, we need to remove generalizability assumption. So, generalizability assumption tells us that there exists a labeler or hypothesis, H star, remember, that will return true label on all of the classes. But returning a true label on all of the classes somehow assumes a true label on all of the samples. I apologize. So that somehow assumes that each of the sample, first of all, can have a label that is unambiguous. It's not always possible. But forget about that. Imagine that a true object in the world can have that label, but the properties or the features that we're measuring may not be able to capture that information, may not be enough. For example, imagine that we want to train a classifier that is predicting biological sex variable from a silhouette, from a shadow of a person. Is that always possible? Well, biological sex variable, biological sex can be predicted or can be assigned to every person because of their DNA. Say, if a person has Y chromosome, then their biological sex is male. There is also gender, but that's too complicated for my example. Let's not get there. So imagine in this situation, we can actually have an f function, f supposed to take an x as an input. So, like, what I'm trying to say is there is a way to uniquely and unambiguously assign this variable, but we don't have access to all possible features, or we don't know which features are relevant to that unique assignment. So we are dealing with silhouettes. Can you predict gender from a silhouette? Well, from a silhouette, as this picture shows, we can't even predict whether it is a human or an animal or like a live thing at all. Like our silhouettes in this picture, thanks to the artist having created that installation, they look human, and we can even tell the gender looking at silhouette, but what is casting the shadow is just this pile of trash. So removing generalizability assumption is tricky. So if we want to release this assumption, which is again existence of such an H star in our hypothesis set, such that probability of the labels that our function returns being equal to the true labeling function equals to 1. So we need to get rid of our target labeling function now, because we can't assume that 1 exists and can label correctly everything. And instead, enter data labels generating distribution. So we have a joint distribution of data and labels, which is our conditional distribution that, given an x, has some probability of generating a y, and prior on the data. So now we're in the Bayesian world, sort of. Well, we're dealing with joint distribution and hey, wake up. Okay. We're dealing with joint distribution, conditional, and marginal. So just a little bit a side note, since we haven't spoke with you yet about those issues. I hope you're familiar with the Bayes theorem and with this general conditional and marginal distributions. Just a little aside. So how do we get there? So we have distribution of data and label, which is the join. So imagine a two-dimensional, right, x and y, and I will deliberately ignore the fact that our x and y both, in our example at least, y is a binary 0 and 1. Let's just, for simplicity of exposition, think about a continuous case. So imagine there is a distribution here somewhere into D that is something one or another. So, and the only thing that we need to know for the following step is that this distribution integrates to 1, right? Over the domain that the distribution defined. So now let's say this is x and this is y. If we fix a value of x, that means that we're taking a slice of this distribution. So when we're saying let's fix that value of x to something specific, xc constant, we are getting the slice of the distribution of y, but in order to get this distribution to a correct distribution from a functional form, we need to normalize it to sum to 1. But to normalize it to sum to 1, we need to take the joint distribution, integrate it over. So let's take d of x and y, integrate it over all possible values of y, which we know is just the marginal, and take it at g of x equals xc, and that will be our conditional distribution, right? If we do the same for the y conditionals, then we can easily arrive to the Bayes theorem, but we will do that later in our course. What I'm trying to say here is that when we replace the target labeling function f with a conditional probability distribution d, data generating distribution d, then okay, just a second. Trying to start my notes. yeah, slightly different exposition. But then before, our loss, or true loss, true risk, was defined as probability with respect to the data generating distribution of our hypothesis not returning a label that a true labeling function would return. Well, but now how do we deal with that? Well, let's redefine now our true loss as probability of the joint. Now, look, that was just with respect to the data generating distribution once we had our true labeling function. Now we get rid of it. We know that it's rarely available in the word processes, but now our D is the joint distribution of X and Y. So probability with respect to the joint distribution of our H is not being our application of our hypothesis to that X not being equal to 1. Or equivalently is probability of a set, true loss, probability of a set, or probability mass of a set of functions x and y for which our labeling function or hypothesis doesn't return a label that corresponds to the true label of the sample. So we want to find in our learning process, we want to find a predictor H that minimizes the true loss, the new true loss. And the problem with this desire is that the learner doesn't know the data generating distribution. In the real world, we rarely know the data generating distribution. So empirical risk remains the same as we defined it before. It's number of incorrectly classified samples over the total of a number of samples in the training set. And now our goal is to find a hypothesis that probably approximately minimizes the true loss. So if we think about it, we already know the answer. Our answer would be the Bayesian optimal predictor. And our Bayesian optimal predictor for data generating distribution, which is joint distribution over our domain with the cross product, set cross product with 0, 1, the label set. And the best predictor is the following. Once we get an X, if conditional probability of getting a label 1 is greater than or equal to 1/2, we return 1. Otherwise, we return 0. I hope you understand that. We will go through Bayesian decision theory later, and I will try to go into the details, but I hope you understand why that is true. If not, think about it, or maybe read some books and refresh your Bayesian learning theory, Bayesian decision theory from the classes that you took previously. But basically, the problem with this was the Bayes optimal or Bayesian optimal predictor is we don't have a hope to find H. Well, that's not the problem, that's an advantage or kind of a property. The Bayesian error is the optimal. There is no way that we can find H with better error, at least asymptotic. But our error is defined as the true loss on all of the data, right? So then the statement is strongly true. Without assumptions on D, no algorithms or D, data generating distribution, no data can be as good as Bayesian optimal. And alas, we don't know D, we don't know data generating distribution, so we cannot utilize the Bayesian optimal predictor, because we don't know what's the conditional probability of a label given the data. Instead, what we want to do, or what we will do, we will search for predictor with error not much larger than the best possible error. So our Bayesian error is the best possible error. So we don't want to be much larger. We don't want to find a predictor that deviates from it to heavier error, larger error too much. Having that, now we can define agnostic PAC learning. Agnostic, probably approximately correct learning. A hypothesis class H is agnostic PAC learnable if there exists such a sample complexity function M sub H, and the learning algorithm with the following properties. For all epsilon and delta and joint distributions of data and labels, when we run this algorithm on number of samples M that is larger than or equal to our sample complexity, and when we run on M IID samples, that algorithm returns a hypothesis or a classifier such that such that the true loss, this is the true loss, is less than or equal to the possibly attainable Bayesian loss plus some epsilon. So we can only hope to get within the best error achievable by the hypothesis class. So this would be the best achievable error, but we cannot attain it, so there will be, well, no. So Bayesian error is absolutely the absolutely attainable good error. And Bayesian error was not defined with respect to our hypothesis class, so we're not considering it. We're just saying, okay, among all of the hypotheses in our hypothesis class, we want an error that is less than, we want an optimal probability of the true loss be less than or equal to the minimally attainable error over all of our hypotheses in the hypothesis class plus some epsilon, and we want that probability to be greater than or equal 1 minus delta. Okay, that is agnostic PAC learning. But there are other problems. With agnostic PAC learning, we have got rid of one large and strong assumption, realizability assumption, that everything can be labeled correctly by somehow unknown to us true labeling function, and we went into the Bayesian world with the distributions that, well, we still use data distributions, so why not embrace it fully? So we embraced the data distribution fully, and just went into joint data label distribution, and now we don't need the notion of true labeling function with agnostic PAC learnable classes. But there are other tasks such as multi-class classifications. For example, we want to classify documents into different categories, or we want to do brain-computer interface with EEG and do implement mind readers or mind typers, so we can type with just our brain waves. The categories from which we want to map our brain waves as our X. We have the whole alphabet plus the numbers to map to, not just two classes. Another multi-class classification is prediction of next word. So there are lots of real-world examples of multi-class classification. Besides the multi-class classification, an extension that would we need, there is a totally different problem of regression. It is fitting well, I would call it a problem of fitting to the data, problem of fitting a function to the data. But usually what we mean by problem of regression is we want to find functional relationships between our X and Y, and where our label, say, is not just a binary label but some dependent variable or a set. So for example, we want to predict age, which is a continuous although bounded number, or we want to predict temperature or any other continuous numbers. So basically in this task we want to find a function that maps X onto Y, find the functional dependence. So regression task is an interesting problem. Basically, when you measure lots of numbers and say you may even have multiple x's, x1, x2, but this y variable is a function of x1 and x2, and maybe we measure this variable with noise, but we need to fit a curve, or in the case of linear regression, we need to fit a line that has a minimal error and can explain the underlying process by filtering out noise. Regression was simultaneously invented by Carl Friedrich Gauss and Adrienne Marie Legendre, or maybe, well, clearly Legendre published it earlier, before Gauss, but there was a dispute who discovered it first, because of the problem that Gauss was solving of predicting, I think that was Luto. Oh well, but in fact, both of them were studying prediction of comet's movement by inexact measurements, and Gauss and Legendre, basically what they discovered is not just a general form of regression, but method of least squares of fitting a curve or a line. In any case, an interesting observation. So, and even from my description, you can see that both of them discovered a method of fitting, and yet we call it regression. And regression is about something that regresses. Like, what is going on? Frankly, I myself confused by the name. Because okay, method of least squares, fine, we use it all the time, But regression, the term that was coined by Francis Galton in the 19th century to describe a biological phenomenon. And the phenomenon was that the height of descendants of tall ancestors tend to regress down toward a normal average, also known as regression toward the mean. But somehow that name got stuck to the method of fitting using least squares. And here's a different example, different examples of fitting different models to the same set of data, to the same set of points. You can use like linear, no slope. Basically, you use the same method but different models. For example, here you're using using least squares method to fit a line to an equation, to a line that has bias and a slope. But here you remove the slope from the function, and you still fit the best or get the best possible fit in terms of least squares. That was all of those fun examples that all of them are showing piecewise regression and all of that. But what is that loss? Least squares loss. So the loss for regression is expected square difference between our true label and what our function or what our hypothesis returns. But since it's very hard to compute the expected square difference, because remember, rarely we do know the d. We use mean squared error, which is just an average error, average squared error between our prediction and our measurement. That's another loss, regression loss, that we can use. So generalized loss function for any hypothesis class H and demeaning Z These are generalized loss is a function from the cross product of our hypothesis set and our domain Z. So for prediction tasks, Z is nothing but the domain where a joint distribution on our data and labels would be defined. But we want to be more general. We want to be Z any domain of examples. For example, in unsupervised learning task, Z cannot be a product of an instance domain and a label domain, right? Because we don't have labels. So we call such functions like the small l, loss functions, and they are mapping to non-negative numbers, right? Non-negative real numbers. So using the loss function, the generalized loss function, lowercase l, we can redefine the risk function. So our true risk is defined as expectation over this z's generated by a data distribution of whatever the loss function returns. And again, the loss function takes a hypothesis and a sample from our domain of interest, and then empirical risk is just the average loss. So that's our generalized loss function. We can also define 0-1 loss using this approach, generalized loss function. So we have our hypothesis as an input, and our pair tuple of sample and label, and we define the loss to be 0 if we correctly, or H correctly predicts the label of X, or to be 1, high loss, if H incorrectly predicts the label of X. And note, for a random variable alpha, which is binary, expected loss will equal to probability of alpha being 1, because it's just integral over all of the losses, all of the 0-1 loss, and zeros don't add up, only ones add up, right? That's clear. We can also define the square loss, which is just the square difference between whatever our function, our hypothesis returns, and whatever is the true value in the training set. And that loss is useful for regression problems. So, slightly rewriting and redefining our agnostic PAC learning for general loss function. So, class of hypothesis H is agnostic PAC learnable with respect to Z, and a generalized loss function L if there exists a sample complexity function M sub H and a learning algorithm with the following properties. For all epsilon and delta and data distributions over Z, when we run the algorithm on M greater than sample complexity, greater than or equal of sample complexity IID samples, and the algorithm produces a hypothesis such that probability of getting a true loss on this using this hypothesis is less than the minimal possible loss attainable in this hypothesis class, plus some allowable loss and accuracy parameter epsilon, and when this probability is greater than 1 minus delta, and again delta is the probability as before of getting unlucky sample, unrepresentative sample that we cannot learn from. And our loss now is defined as or our overall true loss is defined as expected loss, expected generalized loss. So that's it for agnostic PAC learning. That's good.